So this is our 3D printer. The unique feature is that it enables us to take a file that would describe a virtual object in a computer and turn it into a real physical object that we can then use to, not only hold in our hand, but do a real experiment on. This is really all about jamming. So it's really the fact that when the available volume to a bunch of grains gets so small that they get into each other's way, they get stuck.
And it doesn't sound like a very big question, but what shapes would be very stiff or very soft under compression? If you want to build a house, for instance, you're building on a granular material, it might be nice to know what shapes would be good to put on that foundation.
This turned then into a very important next level of research. How to find optimal shapes. If you had just ordinary spheres in 3 dimensions, how do they pack? What if you went away from spheres and had different shapes? How would they pack? That's when we realized that we needed to have a way to fabricate particles of essentially arbitrary shape.
So if you take this shape and you pour a bunch of it into, let's say, a rubber bag, and then you pull out all the air, then you push down on this at the top and you measure, how much force the thing's pushing back with. And to give you an idea, this machine's very sensitive. You can measure everything from how much force it takes to pull apart a drop of water to being able to crush a piece of copper piping from this tube into this little pancake. So what you're looking at here, this is the total force being applied versus the distance that I went out, and then each of the curves is obviously a different sample. If I have a regular solid, like let's say this piece of steel, I can just push on it and measure how much it pushes back. For something like a granular aggregate, that's going to depend on a lot of other things. If I looked at different shapes or different types of ones, they would all have different types of these curves. Originally, the way the research was getting done was we had an army of undergraduates. Each of them had a shape. And you've identified which ones are better or worse, but you don't really have a method to go through this space.
And so that's where Marc developed a fresh approach.
Every optimization, every one of these evolutionary optimizations is going to start off with a random guess. Then as you start to kind of learn where the good results are, it begins to converge. We ran it, we found our optimizer got it dead on. In the case of the softest shapes, amazingly, you find that every single time it's rods. It's always, you just take them all, line them on up, and that forms the softest packing. The stiffest was trickier. You form the stiffest packing shape for a given number of equal sized spheres if you take the most compact shape you can make and then pull off a sphere. These guys are strain stiffening particles. So when you start compressing them, they generate very little force, and they build up more and more force the more you compress them. As far as we know, they're pretty unique in that respect. When we look at it as humans, I think we're surprised by it because physicists and engineers are biased towards looking at designs that are symmetric. The computer and nature aren't.
And in that sense, it is not only nice to find a high performance from this, but it is also particularly nice because it is not something that is symmetric, not something that we would have, as physicists, come up with. With this new tool that we have, we are actually discovering particle shapes that nobody had in particular guessed before. The stress response, the 3D printing, the simulations makes this a complete package for us. That in turn connects to some of the deepest problems in mathematics, physics, and granular physics per se.